Yeah.
So
Yeah, and actually, I think that this is a really important point, especially for students here at Fresno State, because there is not a PhD program here at Fresno State. And so a lot of people, even in sciences, their default is like, oh, I should go and get a master's. Look, I mean, I don't know about you and your experience, but in my experience, very few people get a master's. Why? Because you have to pay to get a master's. And guess what? They'll pay you to get a PhD. It's absolutely right. It is not a lot of money. But going from being a really, really poor college student to only a kind of poor college student, but getting your tuition taken care of, it's a huge game changer. And so absolutely, I mean, I know that a lot of people are like thinking med school route, and that's just another reason to kind of go hard sciences, because they very much so, whether it's physics, chemistry, even a lot of the engineering, they will pay you to go to grad school to get your PhD. It's not something that I think students here necessarily realize, because there's only the master's program here. But absolutely, the PhD route is, I strategically went into it solely because they were going to pay me to do it. And I don't think that that's something that's necessarily appreciated. I will also say, you know, a lot of these internship opportunities come in the form of those emails that we all have a tendency to delete without reading. Okay. The other thing, though, is for me personally, I would not be where I am today if I didn't just decide to look on my school's website, randomly email a professor and say, hey, I am interested in learning more about what you're doing. And that 30-minute meeting just kicked off this whole undergraduate research project that wouldn't have existed if I didn't just take that little bit of initiative, right? Just reaching out and saying, hey, I'm interested in coming to see what you're doing, can start this lifelong connection that all of a sudden leads to you being well on your way to getting a paper published as an undergrad, or some other opportunity like that. So I would say just don't be afraid to put yourself out there and reach out as well, because oftentimes these internships, yes, sometimes they come in the form of these formal applications. Other times they're just somebody kind of sticking their neck out and being like, hey, can I just please come and see what y'all are doing in your lab? That was my personal experience with that. So I didn't know if you have anything to piggyback off of that. Did you formally start in a internship program, or did you just kind of say, hey, can I step into your lab?
I did start. When I was an undergraduate at Berkeley, I found an internship at LBL, which is right up the hill. And I was sort of very lucky to land it, I think. But that sort of got me the research bug. And then I looked around on campus for a research opportunity. But I also spent another summer at another national lab. So I'm a big proponent of the Department of Energy um, summer programs because they pay well and you get a lot of experience. And the other thing I like about them, you guys are all freshmen, but at UCI sometimes a senior will come up to me and say, "Oh, I wish I had done research, but I never had time, and now I'm about to graduate." The Department of Energy also has post-baccalaureate programs as well, where they'll pay you to do research, and then it's sort of a good stepping stone if you didn't get a chance because you were too busy as an undergraduate to get that experience that you need if you want to continue on as well. And those programs pay pretty well as well. So there are a lot of opportunities, but I agree. Sometimes just asking a professor. Oh, the other thing too is if you miss the RU deadline, we do this. Faculty here will do this if they have the money. Is that sometimes if people reach out, past the deadline and say, I really want to work for you. If the faculty have the money, they can put the money out of their own grant, and then they'll just sort of be part. You'll be part of the program where you can get housing and all the professional development, but the faculty member will pay your stipend over the summer too. So that's a way for us to get people in that are past the deadline.
One other thing that you can consider if you guys are freshmen, the way I got into a research lab as an undergrad was I had work study. I was a work study student, and I found a lab my freshman year that was looking for somebody to just help out with lab maintenance stuff, for a work study position. And I knew I wanted to get into research, so I thought, it doesn't matter what they want me to do. That was going to be more interesting than working in the cafeteria, for instance, for me. And so that ultimately, as I progressed on in my college careers, that ultimately led to me doing my senior thesis research in that lab. And there's lots of examples I know of students at UCLA, where I'm from right now, who have gotten entry into their lab starting out as work study and then asking the grad students, the postdocs, a little bit about the science they're doing. And gradually they got asked to do more than just make solutions. They actually got to help out with experiments, and then gradually they're participating in the research as well.
Yeah, my experience was much like that. I unfortunately didn't get the paid position right off the bat. It was a beg to please just let me spend time in the lab sort of thing. And then the nice thing about research is it's really kind of what you put into it, right? If you take time to develop that project and investing your time into it, it can become something much greater than maybe what even that professor had originally intended for you, right? So it's a place where, you can kind of let your passion kind of shine through and develop that sort of thing, and eventually hopefully lead into publication. But I will say, even beyond that, you know what academic research colleges really love? Research experience, right? I mean, it just in general looks great if you plan on progressing on in your education career. That's what they all do, right? They love that stuff. So yeah, I mean, just highly recommend. Just to kind of piggyback off this same thing, college is very much so a time where, yes, you have these classes, you're coming and you're getting these grades. The people who really make the most of their college experience aren't just the ones that go to class, even if they get really good grades. They take advantage of all that other stuff that the has to offer, right? All that other kind of research stuff, all the little extra stuff that they're doing. That's what how you really kind of get the most out of your college experience. Cool.
This is like 100%. I'm always trying to sell research to my own undergrads when I teach them for the same reasons. And you know what I always tell them also is that if they decide I don't really like research and I want to go to pharmacy school or optometry or whatever I wanted to do before, then you have a good letter writer, right? Someone that really got to know you and spend time with you and got to talk to you about science. So that's also really nice too.
And the other thing here, being in the Valley, the other thing that there's a lot of around here is how chemistry ties into agriculture and animal science and that sort of stuff. I mean, there's a lot of ag industry around here that sorry, thought it cut out. That very much so hires chemists. I know a lot of students who go on to do like Apple Lab type tech research positions and stuff like that. So there is quite a bit. I mean, it seems like we're in like this farming community kind of thing. There's a very intimate relationship between ag and science and chemistry. So even if chemistry itself isn't necessarily your bag, but more kind of that animal science route, it's still very much so connected, and especially here. Okay. I will just say the DOE thing, Department of Energy, is pretty cool. They have a particle accelerator in the Bay Area that I got to spend some time working at, and that was one of the coolest experiences of my life. And I didn't even know that they paid well, but hey, that's not a bad thing, right? So,
yeah, actually, you have a lot of options there where you don't have to go too far with Lawrence Berkeley, Lawrence Livermore, SLAC. There's a lot of places up there.
cool. So then kind of segues now. So now you have this research professorship at UC Irvine. How competitive was it to arrive at such a position? Like, what did that kind of look like getting into a research professorship? How long did that take?
So a lot of people do like a postdoc after they do their PhD, and then they apply for faculty positions to this job that I have now. I didn't do that. So actually, I had so much fun working at the Department of Energy National Labs as an undergraduate. That's where I sort of decided that I wanted to get my PhD. And I remember like my first research experience. I went to my boss and said, I want to do this when I grow up. How do I do it? And they said, you have to get a PhD first. But I always thought I would go back. So I did. I worked as a postdoc at Pacific Northwest National Lab. This is in Washington State. And then I was hired as a scientist there, which at the time was my plan. And it was sort of a confluence of different effects, but basically I wanted to come back to California because I was born in LA and raised in LA. And so I moved back here for a scientist position, but it ended up not being a very good position for me. I was sort of like asking around, what else available, and they said, well, UCI is hiring. And so normally it isn't kind of an unconventional path, but I was sort of lucky that some of the faculty here had seen me give a talk, at a couple conferences, and so they brought me out for an interview. But it's a little bit unusual, but in the end, I just felt like I've always sort of done what I've been most excited about, and try to find the right job. And I sort of landed on this one, which has been really good for me.
I don't know if this is true, but I had heard recently that like a research professorship is about as competitive in terms of your likelihood to become one as being a professional athlete or a professional musician. And I, in my experience, they are very few and far between. I mean, you kind of have to be lucky that a particular institution is hiring at that moment in time, or so. I mean, kind of like you were right place, right time when this opportunity opened up. Had a good relationship with the faculty.
Yeah, I think so. I mean, I think that I have a few postdocs that are interested in faculty positions, and in the end, the demographic shifts quite a bit. So a lot of people were hired when universities expanded in the 70s to 80s, and then for a while nobody was hired, and so it was very hard to get a position. But now a lot of those people are retiring, and a lot of schools are hiring again. So we certainly are trying to fill our ranks with a lot of retirements the last few years. Um, but I mean, I guess what I would say, and I tell this to my students and postdocs too, is that there's no perfect job. Like if I one thing about being a faculty member, which is challenging, is that you don't always get choice of location, right? Because schools are not always looking, um, and you're not always the right fit for a certain school, right? I couldn't go like I really, really want to be a professor at Riverside. It might be 5 years before that position opens up. But for me, I was like, I know I want to live in a city. I like California, and I'm happy to do anything where I can do research and lead a research program. So for me, if that ended up being at Lawrence Berkeley or Livermore or in industry, I think I would have been fine with that. JPL, the Jet Propulsion Laboratory in Pasadena. There's lots of places that you can work as a scientist. It's professor is not the end all be all job, although it is fun.
And I guess just to sort of explain to students here, so the typical path that you would take would, as she was sort of explaining, would be undergraduate. You get your undergraduate degree. You go on, you get your PhD, your graduate degree, and then you do what's called a postdoc, which is after you have your doctoral degree, but you're not a quote unquote faculty member. You're just like a full-time researcher that's working at that particular institution. And if or research chops, right? That you can get grants and write papers and kind of run a full-fledged lab before faculty will sort of take that position, take you under that sort of position. So that's what a postdoc is. I don't know that I knew that when I was an undergraduate, but yes, it's just a full-time research position after you've gotten your doctorate degree. Cool. So then, in terms of like people are curious about the day-to-day, about how it works working for a large research institution. I mean, does UC Irvine tell you what to do? Are you following orders from somebody in the department, or is this all really just your creative direction that you get to go with your research? You'd said that you were sort of a good fit for the department. Does that mean that you kind of filled a niche that they weren't sort of researching in, or how does that work?
Yeah, so I've heard people say sort of famously that the best thing about being a professor, you don't have a boss necessarily. I mean, you kind of do, and but you get a lot of freedom to do what you want to do in terms of research. What size group you want to run, and how many students you want to supervise, things like that. You get a lot of freedom in that respect. I was sort of a good fit here because they were looking for an inorganic chemist that had an energy sustainability focus. And so I think like I said, I was sort of on the radar because I'd worked as a scientist and gone to conferences and given talks and things for a couple of years before. And so they sort of asked me, when they found out I was looking for a job, if I wanted to come out. So that was sort of the fit part. I guess I wanted to add something else too about getting the PhD, because I tell this to my students too, is that um, like my students go do lots of different things with their PhD, not just become professors. Some of them have, but about half of them are in industry. So they work at Intel, they work at 3M, Dow, DuPont. And then many of them actually, because we work, I think, in the energy field, actually 3 of them have gone to work at startup companies, right? So that's kind of fun because it's like I always tell them it's a good thing to do when you're young and you don't have too many like commitments financially to do a startup. and then some of them have gone on to teaching positions. And so there's just a wide spectrum. And then I haven't had any students do this yet, but when I was in graduate school, a couple of my colleagues went into management consulting or patent law. They just decided they didn't want to do science in the lab anymore. And it's very lucrative, right? So if you're interested in patent law and you have a science degree, you're very valuable to lawyers. And so they have a very easy time finding jobs, and those that like it really like to do it, you know. So there are lots of things you can do with a PhD that aren't become a professor as well.
Patent law is like probably one of the most lucrative things.
Yeah. I always tell my students if they want to make the most money as possible after they get their PhD, that's probably the way to go. They make a lot more than me.
Hate writing so much that I would rather not do such a thing. But yes, there is a lot of stuff that you can do with a PhD. A lot of times when you're in a research lab, they only know the world of research, so you don't really know all the opportunities that are out there. But it does just open quite a few more doors. I mean, your income earning potential increases quite a bit with that extra piece of paper. I mean, for that reason, if you do have sort of the grades and the time to invest, graduate school can be a very worthwhile experience. And so then just to kind of, like you said, you don't have any sort of a boss, but I imagine at some point, if you're not publishing on a regular basis or you're not getting grants, there's going to be some pressure. Is that just because you can't run your lab anymore, or how does that work?
Yeah, so I always tell my students that my number one responsibility is always to make sure the lights are on and they get paid. So in that sense, you know, I got the comment a lot when I started this job from family members that were like, "Oh, you get summers off, right, as a professor?" And I said it's a little bit different because my teaching is only maybe 30% of my job, and a lot of it is running my research group, and it's kind of like a small business, right? Like I have to put a lot into it to make sure people get funded and paid for their work, that we publish our papers, which helps us get funding in turn again, that they move on and progress for their PhD. So, you know, when I told you that PhDs are totally paid for, tuition and stipend, the PI, which is me for my own students, that's me. I raise the money for that using federal grants, right? So the federal government pays me to make sure research is accomplished, and they pay me to pay students to do that, right? To train students to do that. So these are all federal grant money typically that supports students in my research group to get their PhDs. So it's just a lot of grant writing, managing. It's just like a small business. I have, you know, people, except that I need to also make sure that they're progressing toward their degree, that their career options are open, that they're getting professional development, all that stuff.
And do you have like a personal quota, like this many papers per year means that we're on a good track, or?
No, but I do tell them, you know, what I always say is that, you know, if we don't publish our research, it's like we didn't do it, right? It's like you spent all this time doing stuff. And if we have a conclusion that other people can learn from, we should put it in a paper so that everyone else can read it and see what we did and our conclusions. And I also tell them that, you know, our grants are renewed every 3 years typically. And the reality is that we're evaluated on what we produce, right? It's a product of this investment that the federal government gave us to pay for their education. And so, you know, when those deadlines come around, like we got to get our papers out and things like that, so that when we look, you know, show them that we've done something good with their money, right?
Yeah, totally. So then this is a good segue into now sort of some of the more specific aspects of your research. You know, your presentation kind of had two main components that it was broken into. You know, using the electrocatalyst to convert CO2 to formate and vice versa. You know, sort of broke it into these two chunks here. Could you just briefly remind students, you know, quick elevator pitch on that research, as well as update us on anything that may have developed since your presentation?
So I would say that research is important. So basically, we're trying to figure out how to use CO2 more efficiently, right? I mean, CO2, we can look at it as a pollutant or as a feedstock. Right now, all the carbon that we use in for fuels or for materials all come from the ground, right? We dig it out of the ground and then we release all the CO2, and that has all the climate effects, the negative climate effects. And so, what we're trying to do is very fundamentally understand how to activate CO2, which is a pretty inert molecule, and then how to basically functionalize it to make it more useful. One of the things that we have worked on is formate specifically. And we were interested in understanding the reactivity between formalin and CO2 because, nature is very good at using CO2. And so we're trying to basically see whether we can replicate at least the reactivity that nature does, so that we can better understand how we can apply this to other systems that can activate and functionalize CO2. So that's a lot of the research we do. I would say that, we sort of were trying to make what we would call a functional mimic of an enzyme, right? So an enzyme can do this conversion very efficiently at room temperature, and we're trying to make something that does the same. But when I presented this work to a friend that works at Lockheed Martin on redox flow batteries, he said you could also use this kind of catalyst to make a CO2 battery, right? So a battery that's based on CO2 and formate. And that's an application that I would have never recognized because it's not my field. But because, we talked to each other and talked to people in different fields, he was able to see an application for what we were doing that was sort of beyond what I saw and why we did it.
Wow, cool. And so, this topic is something that you chose because you were personally passionate about. I think you said that you had an interest in renewables even prior to coming to Irvine. So is that that's concerning that kind of kicked this off, or what?
You cut in and out. You wanted to know how I got into this area?
Sorry, this microphone's not doing its job. Yeah, in terms of like what inspired the research, I mean, I imagine it's coming in part from a place of, climate change is this problem that we have. CO2 is this big pollutant that we got to deal with. Is that, did it come from an environmental concern or just kind of your specialty met the needs, or what inspired that sort of direction of your research?
Yeah, so I've always been sort of an environmentalist, and that was sort of unrelated to being a chemistry major. But I would say that my first sort of what opened my eyes to this is that in the summer after my sophomore year, I got an internship at the National Renewable Energy Lab. That was the second Department of Energy internship I did. And I was doing hydrogen research, and it was so cool to me that I could use chemistry to not just make more chemical waste and Superfund sites and, plastics and things, but actually use my interest in chemistry to actually do things that really benefit and look forward in terms of sustainability. And so then I got really interested in that. And so I picked my PhD advisor because he focused on that. And then I've continued to pick projects, and training for that. And then I obviously started that in my own program as well, where I wanted to really focus on, how can we use chemistry to develop more sustainable solutions to different current problems.
And do you see your research as eventually evolving into some sort of a product that could be used to help combat climate change in some way, shape, or form? Or, how do you see the direction of things going with that, hopefully?
Yeah, I do. So, originally we started doing a lot of basic research, but obviously there has been a lot of interest in the work that we do in the last few years. And there's also been a lot of investment by industry into finding, more sustainable ways of doing different processes. And so we actually have started to patent some of our work. And, I've sort of bounced around with different people about starting a company, but I mean, we haven't done it yet, but I sort of have asked the questions like, what do we need to start a company? Like, what kind of metrics do we need to have? What kind of a plan do we need? Who do I need to hire to get that going? So it's sort of in the works, but not anything that's realized yet.
And then, so speaking of, it seems like it's definitely going to be not something that you're on your own researching here. I imagine that it's a focus of a lot of scientists now. And so are there other researchers that are working on this same problem as you? And are you worried that these researchers might solve it first? And, does that sort of influence how you go about doing your research at all?
It doesn't. Partly because I'm really motivated because I want these problems solved. And so I'm okay if someone else like has a better solution. I feel like there are so many problems out there that I'm happy to refocus to other problems and work on that instead. If someone has come up with something better, I mean, in the end, I think I and many of my group members are just motivated to come up with some solutions, and it doesn't really matter actually if it's someone else that has a better one.
Yeah, and I think that's true for research in general. It does suck to get scooped on a particular thing, but nonetheless, actually other people's work more often than not just helps you do better at your job, helps you inform what you should be doing, kind of a path to go down. So rarely is it quite so cutthroat as they published this and now I'm in big trouble. But nonetheless, yeah, I imagine it's a lot of people are working on the same problem from just about every different direction you could possibly think of. And so, this research was very much so inspired by, like you were saying, enzymes that do the same thing. One of the things that about the formate dehydrogenase was this idea that it operated near its thermodynamic efficiency. So we had a lot of students, a lot of groups sort of asking kind of like what the consequences were of that are. Is that something that's very typical for an enzyme or kind of out of the ordinary? And what are the real consequences of its being able to do that?
So, enzymes have to, well, nature in general has to operate well enough to survive. And so they often, what I often say to my students is that for a lot of the two electron reactions like CO2 to formate or CO2 to carbon monoxide, hydrogen, protons to hydrogen, the enzymes that can do these reactions far surpass anything that we have that's synthetic, right? Their performance metrics are much better, and they do it with abundant metals. And that's very important for, of course, organisms that want to stay alive. It pays for them to be efficient, or as efficient as they can need to be to survive. It's interesting that a lot of more complicated reactions that are greater than 2 electron, like water oxidation to oxygen, which is very important in photosynthesis, it's still not very efficient. So this is what plants do. It's called the oxygen evolving complex. And that one is both not very efficient and it's not very stable. So I think that the idea is that enzyme has to recreate its active site every 30 minutes because it sort of gets disrupted. It only turn over so many times. And so that's very energy intensive for plants, right? To collect energy and take water and produce oxygen. And then the other one, that's the carbon fixing enzyme, the Rubisco, I think is the most abundant enzyme on the planet. And it's partly because it's not very efficient. It's not very good at what it does. And so enzymes do have to be good, but they only have to be good enough to survive, I guess. Yeah. There's a joke that we often have said in our group. There's a picture that I found on the internet where it had a field full of solar panels and then a bunch of weeds that sort of grow just over them, right? Because in the end, they only need to be tall enough to survive, right? Which means to go over the thing that are blocking them to compete for the sun. But they don't have to necessarily be better than that. They just have to be good enough to survive.
And so, inspired by this enzyme, one of the things that I found interesting was your transition metal complex that you used didn't really look much like the molybdenum active site of this enzyme. So did you guys explore down the route of using molybdenum? Like, what brought you to that platinum catalyst? Is this, there's some questions, is this largely a trial and error game? Or is this something where you sit down with your calculator and you figure out, oh, this would be the optimal complex here?
So we knew that the best compound would have an energy for hydride transfer that would be close to that of formate. And so we picked the platinum compound because it had the right energy. Obviously, nature doesn't use platinum, and they use more abundant metals like the tungsten or molybdenum. So then the real question is, how do we get from a platinum hydride to a tungsten or molybdenum hydride? So I did have a student make a lot of those analogs. They made compounds that look like the active site of these enzymes. And it turns out that when they're not inside an enzyme, they have all this other side reactivity. They dimerize with each other, they decompose. And so the enzyme really protects these active sites, right, from reacting with each other and from other things outside. And it turns out that it's very hard to synthesize these replicas that behave the way we want them to when they're outside the enzyme.
Oh, so it's actually more reactive in the enzyme complex. It's protected by the enzyme itself from from doing all these unwanted reactions.
I mean, it's, you know, the enzyme's got a lot of spinach on it and it's there for a reason, I guess. This big scaffold for this tiny little metal site.
Was there any sort of idea of just like, let's just harvest a whole bunch of this enzyme here and try to create some sort of like, I don't know, biofilm kind of to accomplish this same goal rather than plucking out the transition metal active site kind of idea?
Yeah, so a lot of people have worked on these bioelectrochemical cells that do exactly that. They basically hook up enzymes into fuel cells or electrolyzers and then have them do the work to be the catalyst. So enzymes are interesting because they tend to have really good activity, but they're also not always stable long term. You know, um, we have platinum often that we use for fuel cells for hydrogen. You could use a hydrogenase enzyme, but in the end, the platinum will last longer, even though the hydrogenase is iron and nickel, right? Um, and there's also fewer active sites per square area for enzymes as well. So people have tried it though. It's definitely something that people have worked on. And in some applications, it might be better for doing this kind of chemistry.
I imagine you're just chewing through a lot of bacteria there to
Yeah.
get them. Cool. So then just kind of turning now to the second main aspect of your research, which was sort of the CO2 capture. It
Mhm.
sounded like you guys were sort of had just kind of, at least in theory, established a working way to do it. Is that something that you guys have since put into practice and have any more updates on for that particular aspect of your research?
That has been a plan. So research moves slowly sometimes. And my student is still working on trying to get that scaled and show it has longer cyclability than we've shown in the lab scale so far. So we are trying to show that it could be more broadly applicable.
Cool. And so, you know, just going down this idea of like carbon capture,
Uh-huh.
like something that in all of our methods of combating climate change, not one that you really hear about as much, even though it seems like kind of the most obvious. Let's take some of that CO2 out of the atmosphere. Is it being discussed more widely than maybe we realize just by listening to the news, or is it something that's got some inherent limitation that we might not know about?
Yeah, so it's become of greater interest in the last year or two. So the Department of Energy has come up with these energy Earth shots, which are these very large, like billion-dollar programs to reach certain targets. And their carbon negative Earth shot has direct air capture of CO2 targets that are, you know, under $100 a ton of CO2 captured. So that has really led to a lot of investment in this type of research. Um, I would say also that there is basically, even though we would like ideally to decarbonize a lot of our chemical processes, there wasn't a lot of incentive to do it before. Companies aren't not going to do things unless they're being paid or it makes sense for the bottom line. So with the Inflation Reduction Act, so you know a lot of the chemistry that we do is heavily influenced by policy, so we pay attention to that. The Inflation Reduction Act that was passed earlier this year gave a credit for captured carbon, and that obviously has gotten a lot of companies interested in developing better methods to do it. So thinking about how to decarbonize certain processes, right? So steel making is 8 or 9% of the world's CO2 emission. Concrete making is also 8 or 9% of the world's emissions of CO2. Um, Haber-Bosch, which makes N2 to ammonia, which makes fertilizer, is a couple percent of our CO2 emissions every year. So people have really invested into how to decarbonize these processes to reduce emissions.
And so it's not necessarily like pulling it from the atmosphere right outside our door here, but rather attaching itself to a specific industrial process that is known to release a lot of CO2 and sort of just preventing that carbon dioxide from getting out.
Yeah, that's right, and it's actually something. So I'm going to a meeting in DC tomorrow, that where we're going to discuss this because there's been a lot of emphasis on direct air capture. Um, I think those of us in the field often, we call it techno optimism. It's like we don't have to stop what we're doing now because we'll figure it out, and then no problem in 20 years we'll have be pulling it out of the air, pulling CO2 out of the air. And so, you understand from your Chem1B that it's easier to pull, the capture CO2 from a more concentrated source than from a dilute source, right? It's better to capture it at a point source than the air. And so it's sort of a misguided, I think, idea that direct air capture is going to save us and we just don't have to worry about things right now. Um, it's probably more logical to think that if we have carbon-free energy to do direct air capture or carbon-free electricity, we should just use that directly instead of in the place of fossil fuels, right? For our current natural gas or coal power plants, right? So if we have the energy, don't use it to capture, use it to prevent emission in the first place. And then the second corollary to that is that if we are going to capture, we should capture from these industries, which we are often called difficult to decarbonize industries, right? So basically, we already have these massive amount of investment in these plants. A company's not going to be like, I'm going to replace my plants with this new process that's carbon free, right? Just not going to do it. So it's better to capture in order to decarbonize these industries than have them change their whole process over. So that's the second thing that I think we should do capture. So concrete is actually pretty easy. It's like 30% CO2. Fossil fuel exhaust from a coal plant is like 15%, much, much easier than air, which is 0.04%, right? For capture, much more efficient, takes much less energy to do it. And so I'm a big proponent of, use renewable energy first to replace fossil, and then if we're going to capture from these point sources that are difficult to decarbonize, and then we can think about direct air, which would be carbon negative instead of carbon neutral. But
And
people like to think about it because of that, like, oh, it'll solve all our problems in 20 years. We don't have to worry about it right now.
and are there any negative environmental effects that have been, that of carbon capture that maybe it sounds like it's all well and good? Is there anything that maybe we're not thinking of that would lead one to be wary about that strategy?
I think all processes are going to have a footprint of some kind, right? You need chemicals to do it. You need plants to do it. Depending on where they're located, that might have an environmental impact um, as well. I'm trying to think like I have a friend that works in direct ocean capture, right? Which is capturing CO2 in the form of carbonate in seawater, which is at least slightly more soluble, higher concentrated than air. And they have sort of the same environmental thoughts of desalination of water, right? Is that stuff lives in water, and how do you deal with that so that you don't have these large environmental effects? So I think anything we do is going to have a footprint of some kind. It's just trying to minimize it.
And then, it seems like even just this past year, country, we had this like delicate balance of energy consumption and distribution in the world that's recently gotten kind of thrown through a loop here, where countries are no longer as, easily satisfied through their oil needs, and sort of are turning more to, just recently in the news, countries turning more towards coal that wouldn't have otherwise done so, or is it seeming like now there's a little bit more of a need of a push to sort of, okay, we're going to have to burn this dirty fuel source, let's just figure out a way to do it responsibly, than there was even a year ago? Or
Yeah, I think that is true. So, they have all these different labels for types of energy and products now. So something that is green is completely carbon neutral, but something that is blue use fossil fuels, but the carbon was captured. And then they have things that are teal, which are a combination of both, so they have different kinds of energy labels now on different products. But companies like to advertise their products as blue or green, depending on the carbon footprint of them. But it's true that we probably can't get off fossils for a while, especially, for a lot of countries, it's just the cheapest source of fuel available, the cheapest source of energy right now available.
and it seems like there's also some unexplored environmental consequences of putting a whole bunch of battery powered cars on the road or generating all those new batteries and stuff. As you were saying, just unintended consequences. There's always going to be some impact somewhere.
That's you're absolutely right. They're hard to recycle. Cobalt, which is in your Tesla or Priuses, there's a lot of problems with the way that it's mined right now. And yeah, that I think from my point of view, just my personal opinion is that we should just try to reduce our footprint, period, right? Like we can't all live in giant houses and drive giant cars and I don't know, like use all these resources. In the end, everything we do is going to have a footprint of some kind, right?
Yeah, the recycling problem is interesting because it turns out that a lot of the wealthier countries will then sell their used electric vehicles to some of the less affluent countries, which kind of get stuck with that. What do we do with all this waste kind of burden? And so I know that that's more of a problem in the developing world than you would think of is what do we do with all these leftover batteries? Yes. So then, I guess, the last sort of question here along this same sort of line is, okay, we were talking about CO2 capture. Are there other sort of efforts to, do other greenhouse gases? Methane being a big offshoot of, industrial agriculture. Is there the same sort of emphasis put on those other greenhouse gases, or is it not quite the fad?
I think there is. And so I think people have recognized that methane is a big problem, has a much higher global warming potential than CO2, although a shorter half-life. And so I think like California, I think they're not going to enforce this, but they now, I think, require all food waste to be put in the green bin for composting. And the reason for that is because the majority of methane emissions come from landfills. And that's just from decomposing food, basically, because it's anaerobic. And so if you can get everyone to throw away their uneaten food and compost it instead of into the landfill, then you can actually reduce methane emissions by a lot. I think they said that they were going to enforce it for restaurants and grocery stores. So we try to do that in my house. We have a worm composting bin, which my kids like because they like to see the worms. But just not throwing away food waste is huge, right? To help prevent methane. We had a project in my group on N2O as well, nitrous oxide, or laughing gas. That is a byproduct of overuse of fertilizers. Also very high global warming potential as well. It's the third largest contributor to greenhouse gases. So there are lots of other things. There's just so many little issues that we have to understand how to deal with, and some of them are easier than others. Like the one that I like so the methane, right? We can do it right by like not throwing away our food waste, and then there is a researcher I saw this talk from UC Davis in agriculture who's found that if you put a certain amount of seaweed in cow food, then they don't burp as much methane. So there's lots of things we can do basically.
And your lab is also sort of looking at these other greenhouse gas emissions as well, not just CO2.
We do N2O, nitrous oxide. We haven't done methane because it's too hard. It's a very inert. It's hard to activate.
Cool. Well, so that's all of our questions that we have for you today. Thank you so much for taking your time out of your day and sort of wrapping up this whole project. I think, as we've gone through the course and learned about transition metals and learned about catalysts and learned about free energy diagrams, all of a sudden your research project, which I think was pretty intimidating and students would admit a little bit above their depth at that point. Now, all of a sudden they could sort of see these pieces. I'll also say that even if you're at the level of Dr. Yang, I'm sure that she goes to seminars and doesn't understand every word of everything that's being said as well. You're always kind of just filling in the gaps based on what you know, and there's plenty more information out there that you have yet to learn. But yeah, thank you very much, everybody. Let's give a round of applause, Dr. Yang, for coming out today. Really appreciate it. Cool. And Ira, was there a survey that you had sent out as well, or?
Yeah, so if you guys can just take a few more minutes, maybe about another 10 minutes here to complete a post-course survey. So yeah, my name is Ira Clark. I'm at UCLA. I'm the lead PI on this project that it's being funded by the state of California. And it's a collaboration with Fresno State, UCLA, and Glendale Community College and Santa Monica College. And the whole idea is to try to see how impactful it is to introduce research into introductory courses like Chem1B. I think you all took a survey at the beginning of the course. We have a survey now at the end of the course. It should have been emailed to you within the last hour or so from an email address that is assessment@teaching.ucla.edu. The survey is voluntary, but we really appreciate if you will participate in it. And I believe that Dr. Corsipius is awarding a few extra credit points for participating in it. It will help us understand how impactful this project is, what's working, what's not working, how to improve it, and really help out your fellow future students in future classes where we try to, hopefully continue this approach of embedding research into introductory coursework.
Awesome. And you said
I just want to also mention that Dr. Corsipius neither Dr. Corsipius nor I nor any other faculty will see any of